Okay, so for those of you who are here today, we are going to talk about a very important topic, which is a very widely used technique in statistical modeling called the expectation maximization algorithm. So we will introduce it in the context of our mixture model-based clustering. So recall that we have talked about multiple clustering algorithms. We started from k-means, and we talk about its extension to graphs called the spectral clustering. Then we talk about the hierarchical clustering. These are all algorithms that can operate on our n observations to divide the n observations into a number of clusters. But they don't assume a probabilistic model to achieve the clustering. In contrast, this mixture model-based clustering relies on a probabilistic model. It will try to fit the model to data. That means it tries to estimate model parameters from data. And then given the model parameters, the model-based clustering will provide a natural way for assigning each observation to a cluster. So let's say that here we call this I the ith observation. It's p-dimensional feature vector, which means that the p features values in this observation is denoted by xi. Then given this xi, what we want to infer is the latent label zi. Zi takes values from 1 to k. In this case, we are assuming that we know priorly that there are k clusters we want to assign to. So you still need to have that choose k problem here. And then you want to estimate this probability. Some people call it posterior probability, which is about the probability that zi takes value k. That means observation I is assigned to cluster k, given its feature vector. So with these values, right? So for each I, let's say we have this probability for k goes from 1 to big K, then we can assign observation I to one of the k clusters. One way is that we do hard clustering. We assign I to the cluster that maximizes this probability. Or we can do soft clustering. That means we allow observation I to belong to all the k clusters with different probabilities. So this offers a very good framework. But the problem here we're facing here is a technical challenge. How do we estimate parameters of this model? So we start with this simple, I would say, two-class normal distribution model or two-class Gaussian mixture model. Here, we just have Zi takes, so here I changed the notation to 0, 1. So Zi equals 0 is one cluster or one class. Zi equals 1 is another cluster or another class. And then in each class or cluster, the distribution of Xi is following a normal distribution. And here I'm simplifying the story by making the dimension of features to be just 1. So here xi is just a scalar. Okay, so with this model, how do we estimate the model parameters? And here the parameters include p, the proportion of class 1 among the two classes. The mu1, mu0, the two means of the two normal distributions, sigma 1 squared, sigma 0 squared, the two variances of the two normal distributions. So these 5 parameters need to be estimated. So last time I gave you a review about how we do maximum likelihood estimation if we have the complete data, which means that we observe both xi and zi. They are all observed. So in this case, how do we estimate those 5 parameters? We did the MLE, try to write down the likelihood. Here is the key. The likelihood is basically the joint density of my data at this parameter value, theta. So we can look at this function in 2 ways. If we consider the data x1z1 to xnzn to be the variables in this function, then we call this, and theta parameter being fixed, then we call this joint density. If we look at another way, we consider the data points x1z1 to xnzn as fixed, but we vary theta, then we call it a likelihood. So in this case, this likelihood function is fully specified as a function of theta if we input our complete data. Okay, and then we try to maximize this likelihood. That's our goal. And to maximize it, it's easier to take the log of the likelihood first, because this can change product to sum and remove any power functions. The power will come down. So we get a log likelihood, and then the remaining task is to find the values of P, mu1, sigma 1, mu0, sigma 0, so that this function of theta is maximized. And the result we get is simply these formulas, which make a lot of sense intuitively. So P hat, the estimated P, is just the proportions of zi's that are ones. And the mu0 hat is just the average of the xi's for which zi is 0, and so on. So we obtain those estimates from complete data. But the challenge is that we don't have complete data. Otherwise, we don't need to do clustering, right? If we know the zi for each xi already, why bother doing clustering? And so here, z1 to zn are unobserved. So they are latent data. People call them missing data, latent variables. Either way, they're just some names for those zi's. So in this case, you have this missing data problem. You only have x1 to xn. Then how do you estimate the parameters? So if you understand the likelihood of theta is defined as the joint density of data given theta, then here the likelihood should be changed to this joint density that is about x1 to xn only and not involving z1 to zn. So how do we obtain this joint density of x1 to xn only? We could still start with the joint density of x1 to xn and z1 to zn. But we can integrate out zi's, z1 to zn. So we are left with a marginal density, I would say the density of x1 to xn. So what I'm saying here is this basic fact. So this fact is that if you want to obtain the density of x, right? But you start with a joint density of x and y. Then what you can do is that you can just integrate out y, and what you get is the density of x. So what we're doing here is exactly the same. So we are basically doing this. So the f x1 to xn theta, which we have for the likelihood for this incomplete data, can be written as the joint density x1 to xn, z1 to zn, given theta, this joint density, and we consider all possibilities for the zi's. So here, let's say z1 can be 0 or 1, and zn can be 0 or 1. So for z1 to zn, we have n of them. Each has 2 possible values. So this sum is actually over 2 to the nth possibilities for z1 to zn. If we add them up, then what we are left with is just the joint density of x1 to xn given theta. And that's our likelihood of theta. So assuming that we could do this computation, you could imagine that it's quite difficult. Then we are left with this likelihood, and then we can do the optimization. But as I said last time, this likelihood maximizer is difficult to find. The reason is because we have 2 to the nth possibilities here. So what can we do, right? That's the problem. Okay, so another way to think about this problem is that if we can actually obtain some relationship between that easy problem we already solved, the complete data MLE, and our missing data, if we can make the connection there, then probably we're okay. Okay, so that's the whole goal. So basically the EM algorithm, the expectation is actually taken over the fact that we are going to do an expectation in some way. And then we are going to, in the second step, maximize that expectation. So hopefully we are able to maximize this likelihood, our target. So our target is still the same. We want to find its maximizer and call the maximizer the MLE. But the question is how to find it. So instead of doing this brutal force optimization, we can find a smarter strategy. And that's the EM algorithm. And that's what we're going to introduce today. Okay, so before talking about the EM algorithm, we can talk about something more general, which is just a philosophy in optimizing a complex function. Okay, so the philosophy is like this. So if we have a function, let me see. If we have a function like, okay, I'll just call it using our same notation, theta and L theta. So if we want to maximize this function, so let's say that the function is like this, and we want to find its maximizer, right? So this is the value we want to find. But this function itself is difficult to optimize. For example, it's not easy to take, it's not differentiable. We cannot take the first derivative. For reasons like those, then we need some strategies. And a common strategy is that if for every value at theta, let's call this theta t. T means the tth iteration, okay? If you can find a function that is less or equal than this L theta, but it's tangent to L theta at theta t. Okay. Okay, so for a function like this, let me call this function, call it say h of theta given theta t. So it is a function of theta as well, but I'm put given theta t as a mark here just to make sure this function and this L function are equal to each other at theta t. So in other words, what this means is that it says that two things. One is that L theta always dominates this h function. Okay, so h function is a lower bound. And second, the two functions are equal to each other at theta t. Okay, so if we can find a function h like that, and if this h function can be easily maximized, okay, and if h, I call this dot. Dot means that this is an argument of this function, and this argument can be anything. So I said if this can be easily maximized, okay, and I will call this maximizer theta t plus 1. So if I call this argmax h theta t, theta given theta t, and I'm going to optimize theta. If I call this maximizer, then what I would have is a very interesting relationship. That is, I can claim that at my original function to be maximized, the L function at theta t plus 1 would be increasing. So this L theta t plus 1 would be larger or equal than the previous value, L at theta t. So this is the most important result, and this is the philosophy behind EM algorithm. So how can we derive here? The key is this tangency. We need this, otherwise it cannot get through. So basically, the proof for this statement is just one line. Because of the dominance at this new value, theta t plus 1, L should be greater than h, right? Greater or equal than h. This is by the nature of dominance, that h is a lower bound. Okay, and then we know that this theta t plus 1 is a maximizer of h. Hence, h theta t plus 1 should be larger or equal than h theta t, right? We have this relationship. And finally, because of the tangency, we can have this equal to L theta t, right? This is due to the tangency, and we're done. So basically, without the tangency, due to the upper bound nature, the last equality would be less or equal than. Then this whole inequality would not go through. But fortunately, due to the tangency, we can have equality in the last step. So we would have this increase in L, which is what we want. So therefore, the whole idea of this optimization, this iterative optimization, is that at every step, at the current value, we find the lower bound, which is tangent to the target function at the current value. And then we optimize this lower bound. This can ensure that our target function is also increased. And then we go from t plus 1. We do another lower bound tangent and t plus 1 again and again until we cannot further increase. So due to this climbing up nature, we can show that this approach can guarantee this iterative approach is guaranteed to converge to a local maximum. So you see why we say this is a local maximum instead of global maximum? The reason is this. If your L theta has more than one local maximum like this, okay? So if this is the L, and if you start from theta t here, then the best you can do using this approach is that you will reach here. But once you reach here, you will never go down. So you will be stuck here. So that's the reason why this approach will guarantee that you always climb up and never climb down. But the drawback is that once you reach a local maximum, that's not a global maximum. You can never get out. That's the problem with this approach. So what's the fix? The fix is that you just have to try several initialization. Hopefully that one initialization can lead you to the global optimum, global maximum, if the function doesn't have too many local maxima. Okay, so what I just introduced is called the minimization. Oh, sorry, I should say, let me see, is it called, it's called minorization, like that. Minorization maximization algorithm. Many people call this in short as MM algorithm. So here the minorization is saying that the lower bound we find is a minorization of the target function. And the second step is that we try to maximize the function. So here the minorization step, let me just go one more detailed step to say, the minorization step is to find this H function. To find H function at theta t such that we have L theta always dominate this H function and L theta t equals H theta t. Okay, so this is the first step. We want to find this H. And the second step is maximization, which is to maximize H. So we update theta t plus 1 as the argmax. Okay, so that's minorization, maximization. And this is the maximization problem. If we take the inverse of the function, the target function, then we can turn this problem into a minimization problem. And then the minorization will become majorization. Okay, so which is equivalent to another name for the MM algorithm is called a majorization, minimization. Still MM. So what this says is that if you have a function to minimize, so let me call this negative L theta, the function you want to minimize, and then at the current value theta t, what you need is to find an upper bound of it. And the upper bound must be easily minimizable. So the upper bound may look like this, okay? Tangent with the target function theta t. And then you will move to the minimizer of this upper bound, and you call that theta t plus 1, and you go this step. So it's just reversed. Reverse this minimization, this minorization and maximization algorithm, right? So you just need to know one and the other become natural. And I want to say that this MM algorithm, both versions, should be attributable to our faculty, a faculty member at UCLA, Ken Lang. So he is the basic inventor, I would say, or at least he made it popular in the whole community. He introduced this algorithm and gave it a name. So, and this algorithm is just generally applicable in optimization problems, especially when you have this one-dimensional function you want to optimize, right? In this case, you have a very clear idea about how to find the minorization lower bound if you want to do the maximization. Okay, so I want to say that the EM algorithm we're going to introduce today, EM algorithm is a special case of MM algorithm. Okay, so what we aim to do is that we're going to express the expectation step as a way to find a lower bound. Okay, so in other words, what I want to say is that the expectation step is to find a lower bound of L theta, our likelihood function, given theta t, which is our current parameter estimates, okay, EST. So let's say it's an iterative algorithm. Let's say we already finished t iterations and we have this current estimate called theta t. Given that, and given our likelihood function to be maximized, we want to find the lower bound. And the second step is to find the maximizer. Maximization is to maximize the lower bound to find theta t plus 1. Okay, so I would like to say that the EM algorithms has many introduction tutorials if you check online. And I found some of them not very easy to understand because you will see a lot of formulas there. So it's quite complicated as it seems. However, I want to say the underlying logic is not as complicated as it seems if you understand MM already, the minorization maximization algorithm. All right, before I start talking about the EM algorithm, do you have any questions so far regarding the MM algorithm, the general idea behind it? All right, if not, then I'll continue. So regarding the expectation, now let's think about our target function, okay? So I will simplify my notation a little bit. I will just refer to my feature vectors of my n observations as a set X, okay? And I will refer to the latent labels of the n observations Z1 to Zn as Z. So this can simplify my future discussion notations. So you know that we actually have the complete likelihood, which uses the latent data. Okay, so that's what we did in the MLD. This is our MLD target in the complete case. So when all the ZIXIs are observed. So in this case, the complete likelihood we still write as we call LC. Okay, C stands for complete. Is defined as the joint density of X and Z given theta. Okay. How about our likelihood? The likelihood is our real target in the missing data case, right? When Z is unobserved. So in this case, I will write it as L theta, which is the density of X given theta. Okay, so as I said, we could always write this as a sum of this one, right? We can integrate out the z. But another way to write it is that we could actually write this. So as I said, one way is to, right? We could do this. But another way, another step we can go further is that we can write it as some expectation of z. If we factorize this joint density, or sorry, I think I forget this theta. I should stay here. Factorize this joint density as, if I do this, fx given z and theta times fz given theta, right? We can do this, right? And then you can see clearly, this is what? This is just an expectation. So because we are having a function of z here and times the density of z dz. So this is what? This is expectation of fx given z theta. Okay, we can write it this way. And this expectation is with respect to z. Okay, so we are taking expectation for z, and then that will be our likelihood. Okay, and then one more step, what we can do is that you can see when we take expectation for z, essentially, an interesting thing is that if we actually change this theta to a particular value, say our theta t, then this whole expectation is with respect to the distribution of z given theta t. So maybe I should put it clear here. So the distribution of z is given the parameter theta. That's what we start. Okay, so this is just using the definition of expectation, nothing special. So for example, to give you the fact, it's just like if we do this, any function of z times the density of z given theta dz, this is defined as expectation of gz. That's it. Okay, so what else? Another important thing is that to maximize this, what we usually do is the log likelihood. That's a necessary part. Otherwise, the EM algorithm doesn't go through. Okay, so for the log likelihood, what we are doing is called the small L theta. So if you believe this follows, then it will become log function of this expectation. Expectation of z given theta f okay, this is it. Okay, and also I want to say that as we know, for this factorization, when I get this z out, what we can say is that this z can follow any distribution as we want. So basically, if we regard this as expectation, then this expectation for z can be conditional on theta, or it can be conditional on theta t, a particular value. So that's the thing we're going to use next. But for now, we can just think about this log likelihood as a log of an expectation. And now it comes, we will use an important result or inequality called Jensen's inequality. So Jensen's inequality is a very useful thing in statistics when you deal with log likelihood. The reason is that the log function is what we call concave. Okay, so if we plot this log function, and here say let's just the positive part. So the log function above 1, it should look like this. And we say it's a concave function. And concave means what? If you draw a straight line between two values, the straight line will be below the curve. That's how we define a concave function. So a property of this concave function is that intuitively you can see it. So if I call this A, if I call this B, okay, and if I take the average of A and B, what I will have, this is A plus B over 2, okay? And then at this average, you are going to have the log at the average above the average of the log. Okay, the reason is that in the y-axis, this here is just log A. Y here is log B. And if I take their average, the average lies on the straight line. But if I take the average of A and B first and call it A plus B over 2 and find its corresponding log value, it's above the straight line. So that's why I have here. So with this intuition, then you can replace the average by expectation. So Jensen's inequality basically says that if you have this intuition already, it basically says that for random variable x, then the log of expectation of x is greater or equal than the expectation of log of x. Okay, and here for the A and B, it should be strictly positive, strictly greater than. But here we have this equal sign. The reason is that if x takes only one value, so expectation of x, if x is just not random variable, but a fixed constant, then these two sides will be the same because you don't need expectation anymore. Expectation can be removed. So this is Jensen's inequality. And you see here, if we apply it to the log likelihood, what happens? Then if we exchange expectation and log, as we do here, we found the lower bound of the log likelihood. And that's the key message. So let me go to next step. So if I turn the page and say that by Jensen's inequality, we would need to do what? We would need to just write the log likelihood, L theta, which is the log of the expectation of z given value theta of f x z theta. Okay, and this is larger or equal than if I get expectation out. Expectation of z given theta log right? This is what we have. Okay, and then what's next? It says that we find this lower bound, and this lower bound is still a function of theta, right? And so we basically have two functions of theta, one on the left, one on the right. But do we satisfy that tangency? Under which case can we satisfy the tangency? So back to Jensen's inequality, we're saying it's the tangency holds, right? This becomes equality if x is not a random variable, if x is a constant. Okay, so this happens if x is a constant. It doesn't vary, its value doesn't vary. So then let's come back to here. What is our random variable? It's actually about the z given theta, okay? So under which case is the z given theta a fixed quantity? Or here we don't care about the randomness, or I shouldn't say that. I should say, given the distribution of z given theta, when is this fx given z theta, this quantity a constant? That's the question we want to address. Okay, so then when does equality hold? That's the case that fx given z theta is a constant. It no longer varies. And then let me ask you the question. What is the random variable in this conditional density I wrote here? Any idea? Okay, probably I didn't make it super clear. So the equality hold, maybe I should say, when does the equality hold at theta equals to theta t? Let's say that we already finished t iterations and then we want to continue. Z, yep, Z will definitely contribute to it, right? But here the thing is that we are considering, yeah, I think you made a very good point. So basically when we take the expectation of Z out, we are thinking about that, yeah, in this conditional density, Z will be integrated out, right? So therefore, yeah, if that's a constant regardless of T, regardless of Z, then we're good. So basically we are saying this. So the constant, this means that f x z theta, okay, is a constant and doesn't depend on z given theta t. Okay, this is what we want. Oh, I should drop it here. Yeah, doesn't depend on the z given the current value t. So basically what we need is this. So we will need that for the L theta at theta t, the current value of our log likelihood. If you write it, let's say that this theta can vary, okay? But inside it, here, we would keep this at, we will need this theta t. That's the function we have. And we want this to be equal to this. So the key is that we want to find the distribution of z given theta. Find the distribution of z given theta such that we have this equality, okay? Such that this f is just a constant. This is what we need. And I think probably one thing I think which left as a gap is I think I need to write down the previous sentence complete instead of just saying it. So what I really mean is that if you think about this joint density, this thing, if we think about it and we factorize it, so here the thing is that we can treat this x and z like this. So we still keep it as this, but for the z part, we can let it vary. So for example, this theta t could be its own theta t, and then as long as we do the integration, we are good. I don't know if I make this super clear, but what I really want to say is that probably I think I tried to teach it differently this time, but I think I messed up the notation a little bit. Sorry, forgive me. So I think what I really want to say is this. Okay, so is that given this joint density, depending on theta, this is what we're interested in. And what I want to say is that, so if I let, say, G, okay, be any density of Z. This is what I want to say. So here I'm abusing the term a little bit. By density, it includes probability mass function because here the Z is just discrete. But regardless of that, what I can say is that I can always write this as fx given Z and theta times the density of Z alone. Okay, this is always what I can write. So I'm just factoring this as a conditional density and some marginal density. So therefore, I can always say that if I want to just get the density of x alone, I can always say that I'm doing the integration. Okay, And then I can always say that it's the expectation of fx given z theta for any distribution of z. And here z follows g. Okay, that's what I mean. And then the question is, recall that we are dealing with a log likelihood, right? So now coming back to, so probably I can say this is a new start. And with this, and then let's say that for the log likelihood, which is written as L theta, and in our incomplete data case, it's the log of the density, right? It's this. So therefore, it's log of the expectation of z following any density g of fxz theta, right? And then by Jensen's inequality, we will get a lower bound of it. And the lower bound is still expectation of z following g. Inside expectation, I have log okay, that's it. This is what we have. So this is so far where we get it. But the problem is that, let's say at a particular value theta t, we want equality. We want equality in this step. Then how can we do it? So under which distribution of z can we have this fxz given theta a constant? Find g, okay? And it turns out that the answer is z should follow this distribution. The conditional distribution of z given x and theta t. This is the answer, and this is what we will have. And why is that? The reason is if we have theta equals to theta t, okay? So then basically, we would have fx given z and theta t, okay? We will have this. And this is what? This is like if we use the Bayes rule to do it, we can write this as just some density of, let's just use the same notation, f of z given x and theta t, okay, times fx given theta t. And what else? And we're going to divide the fz given theta t, right? This is what the Bayes rule is doing. And now you can see that if we set a g function to be like that, so if we set the gz, okay, to be just like fz given x and theta t. All right, and let's move back to the expectation. Then what we would have is the expectation for this. Okay, would just be equal to, if you recall, we have above here, this is what we have, right? So this is the factorization. So we are going to do the f at x given z theta t, no problem. And then the g will come in, and g is f of z given x given theta t dz. Okay, and this is what? This is just, if we open it up, we are just having fx given theta t. And that's exactly our likelihood at theta t. So basically, you can see that with this expectation, if we take it, we restore the likelihood on the left-hand side, right? And then on the right-hand side, what we are going to have is that as long as the Jensen's inequality holds, so basically we are going to say that here, this thing, following this, then we have, let me see if I have missed anything. We have the expectation as a constant, sorry, we have this as a constant regardless of the expectation of z. So basically, with this inequality goes this way, then what we will do for the right-hand side right here is that this one, the right-hand side, let's say we have the log fx given z and theta. Okay, on this side, what we have is that it can be written as log of log of x. Let me see. Log fx given theta divided by fz given theta. So we would have here. And the thing is that if we already have set the distribution of z, which is g, to be z followed in theta t, if we set it this way, then what we have is the right-hand side is maximizing the right-hand side in terms of theta is simply equal to maximizing the complete log likelihood of theta. This is what I want to say. So because this distribution of z is given on theta t. So basically here theta is not involved. So what I mean is that if we want to find the argmax of this log fx given z and theta, in terms of theta, it becomes the same as finding the maximizer of log of fz given theta. Okay, and this is just the argmax of the complete log likelihood. So I'll just write log as ALC, complete log likelihood of theta. So this addresses the maximization step. So we have the under the lower bound step, right? So we say that moving the expectation out of the log will give us the lower bound for this log likelihood. And then to maximize this lower bound, we just need to maximize the log complete likelihood. So this is the magic of EM algorithm. Basically, we find a way to utilize our previous answers from the complete data. So we can use the complete data MLE to address the maximization step. And for the expectation step, we can find the lower bound. So I don't know if I made it super clear, but expectation step, the lower bound, is equivalent to the minorization step in MM algorithm. So our goal is that given the current theta t value, we want to find the lower bound of this log likelihood, this L theta function, and using the Jensen's inequality to find the lower bound. And we found that to make the inequality become equality at theta t, we just need to set the distribution of z to be equal to the posterior distribution of z given x and given theta t. Okay. So any questions before we move on? Basically, I'm talking about the underlying reason behind the EM algorithm, why it works.
Can you explain how that line that reduces the expectation
Yeah.
to, yeah, I think that I'm just missing that step between the second and third equality.
Yeah, I think so. I think I also think I didn't make that super clear, I think. So basically, I would say that here the equality only holds at theta t, right? At theta equal to theta t. So what we want, let me grab another piece of paper. So regarding the tangency at theta equals to theta t, what we need is the log, of this expectation given this function, any distribution of z called g of this f x given, okay, theta t, right? Okay, I need this to be equal to expectation of z given g log f x given z theta t. Okay, this is what we need. Theta is equal to theta t. And then what I want to say is that if we set, and also here the expectation is taken over z, okay? So in this case, we are regarding z as the random variable. So z is the random variable. Okay. And then what I want to say is this. For this function inside expectation, f x given z theta t, for this thing, I'm saying that based on the base rule, we can write it as f of z given x and theta t times fx given theta t divided by fz given theta t, right? There's no problem with that. But then what I'm saying is that it's basically a form of this, sorry, I think I want to say that the randomness comes from z. So I think maybe one thing I think probably it's not really about the constant thing. Sorry. Okay. Right. So yeah, I think I missed one term, probably out of that. Okay, so I think I made a mistake. Sorry, I think I have to apologize. I made a mistake from an early step, which is what I have here. I think this is the step where I missed something. So basically, to re-clarify what I said is that basically, I think what I missed is a crucial step. Sorry about it. Sorry, I'm trying to teach this out of my mind, but even though I thought I'm so familiar with this, but still, I just had this slip off my mind. So what I'm trying to say is that given this complete likelihood, right, and what we want to write is that this can be written as, okay, this should be correct, fxz theta divided by gz times gz. Okay, this is g is any density of z. This is the key. I cannot just simply write this as the conditional, because if g is not really following z, following theta, then that's wrong. So I made a mistake from there. But now with this, right? And then this is what we call the complete likelihood. No issue with this. That's right. But for the likelihood of theta, it's defined as fx given theta, right? So we don't know z. And then this can be regarded as the integration of fx z given theta dz. We integrate out z. And now I put the above formula back. I'm getting, oops, sorry, given theta gz, dz. All right, since g is any density of z, now I write this as the expectation of g following z of what? F x z given theta divided by gz. Okay, this is the expectation. And now I'm going to the log likelihood. Okay, which is just log of this term. xz given theta gz. Okay, and then by Jensen's. By Jensen's inequality, this will be expectation of z following g. Of z following g. Inside expectation, I have the log. Log of this ratio. Okay. Right, we are here. Now the question is, at theta equals to theta t, how can we make the equality? At theta equals to theta t. For what? G, is this ratio a constant? Okay. By having it a constant, what do we have? What do we mean? It means that if it's a constant, it has nothing to do with z, right? Z is the randomness, where the randomness come from. If this ratio has z removed, then we see it's a constant here. Okay, it's a constant with respect to the randomness of z. Okay, and now the answer is gz must be equal to the density of z given x given theta. Okay, this should be theta t, given theta t. That's it. The reason is because with this gz, then you can see that the ratio right? It becomes just x, fx given theta t. This is by the product of joint density equals to the conditional density times the marginal density. And this has not unrelated to z anymore. So that's why it's a constant. There's no randomness anymore. Right? Does that make sense now? So basically, if we have this right-hand side, so basically we would have L theta t equals the right-hand side. Here, the right-hand side is that if we let z follows the conditional distribution, as we said above, right? This conditional distribution given x and theta t, then the left-hand side equals the ratio on the right. On the right, I have the log fxz given theta t divided by f, right, divided by f, and that gives me z given x and theta t. That's it. Okay. So one important thing is that this argument for the tangency gives me g. So with g specified in this way, so the lower bound I find is, so with gz specified as fz given x and theta t, we have the lower bound of the log likelihood. The lower bound here we want to maximize is just the expectation of, still it's about expectation of z, right? Following this, f log fxz. And here it's still theta, because here we're talking about general theta, but gz is going to be put down here. And in the gz, theta t is used. Okay, so that's our right-hand side. And then if we want to find the maximizer of the right-hand side, so maximizing this, I call this right-hand side. So therefore, what I'm saying is that if find and the right-hand side is of course a function of theta. Theta is in the numerator. So I'm saying is that argmax of this theta of the right-hand side is equal to the argmax of theta of this conditional expectation, right? So now theta follows that conditional expectation. So it's equal to maximum expectation of z following f of x given theta t of the numerator log. Okay, that's it. Because the denominator doesn't involve theta, so we can drop it, right? It's a log of numerator minus log of denominator. And log of denominator has nothing to do with theta, so it's gone. So is everything clear now? Like Aditya, does that answer your question?
Yeah, I think that makes a little more sense. I'll just have to go through it after just a little bit more methodically. Thanks.
Yeah, so basically everybody can just start from here. Yeah, because we just redid everything except our introduction to the Jensen's inequality. So the key is to write down, I would say the key is to write down the likelihood we want to maximize as some expectation of z, of the latent variable. Okay, and we say that actually this Jensen's inequality makes any distribution of z called g hold. Yeah, I think this is wrong. It should be z follows g. Any g can hold this, have this Jensen's inequality hold. But to make the tangency hold, we need this ratio to be unrelated to z. And we found that if we let z follows this conditional distribution given x given theta t, then this ratio is not related to z. So therefore, we have that minorization satisfied in the MM algorithm. And then we maximize the lower bound. Here, the lower bound to be maximized turns out to be maximizing the expectation of z, conditional x, conditional theta t of this complete log likelihood. Okay, so to summarize the algorithm aspect, right? So in the E step, what we will do is that given the current parameter value theta t and given the log complete likelihood, which is what we wrote as log of the joint density of x and z given theta. So given those two, we compute this expectation of z given x given the current value theta t of this log likelihood. Okay, so theta stays, but theta t will also enter because that's how we compute the expectation. And second, my M step is to find the maximizer of this function in terms of theta. So we find theta t plus 1 equals to the argmax okay. So I think the most confusing part about understanding the EM algorithm is you need to be very clear that when we write a function, what its argument is. What's the thing we want to maximize? That's the key. And also when we talk about expectation, what's the random variable? So I hope that maybe I can use the concrete case to make it a little more straightforward. So basically, if I come back to, let's see. If I come back to the complete case, right? So in our previous example, this is a complete log likelihood if we assume Z is observed. All right, so we start from here. So in our case, let's say that in back to the GMM, Gaussian mixture model case. So what I was saying was the general EM algorithm. Back to this case, then we can have the complete log likelihood, or we say log complete likelihood. I think that's more accurate. The log complete likelihood is just this, right? So this is what we had before. And that's it, right? So we have it, is available. Now the E step is that we already have some initial estimates of the 5 parameters. Let me call that PT, mu 0t, mu 1t, sigma 0t, and sigma 1t. We have those 5 values already. Then you can see that if we do that expectation of log f x z at theta t, okay, and this expectation is for z following that density of z given x and theta t. Right? If I do that, and then you see, this is the log likelihood. I'm going to input here. So then basically, what I will have is that the summation will go in I from 1 to n, okay? And this is about z. So zi will stay here and multiply by some terms I'm not going to write down, plus 1 minus zi stay here, plus some other term here, okay? So if you simplify the structure and only look at the zi's, this is it. So then therefore, the expectation is only about z. Z includes z1 to zn. It would just enter the summation. So what I would have is that I will have the sum I from 1 to n. And then the zi will have expectation around it. Expectation of zi given x and theta t times this dot 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 term plus 1 minus expectation of zi given x and theta t, okay? And times the other term I ignored. That's it. So basically, you can see that this is what? So if I call this previous log likelihood as about x and z, which is here, right? So just in the old notes, this is log f x z given theta. If that's it, then after I put expectation inside, I'm just having this equal to log of f, x is still x, but for z, I'm not doing z, I'm doing the expectation. Expectation of z given x theta t. These two things in the joint density. So that's why in the EM algorithm, a way to simply put it is that you are still doing your log likelihood as in the complete case, the log complete likelihood. But in the complete likelihood, you are replacing the latent variables z1 to zn by their conditional expectations given x1 to xn and the current parameter value. So therefore, if we use the formula we obtained before, the formula right here, then you can see that in the EM algorithm, so let me do this. So in the M step, if you want to maximize this thing, it's the same as you can obtain the same MLEs, but not based on ZIs anymore, Instead, you are using the expectations. So here, I'm going to say that here the P plus 1, the updated proportion, right? The updated proportion would just be equal to 1 over n summation of expectation of Zi given x, given theta t, given the current parameters, okay? And mu 0 hat will be similar. So in the denominator, I will have summation I from 1 to n, 1 minus expectation of Zi given x theta t. Okay, in the numerator, xi times 1 minus expectation of Zi given x given theta t. Okay, so and everything follows and so on. So in other words, you can sort of regard the EM algorithm, you can think of this E step as sort of kind of equal to imputation. So you are imputing the latent variables Z1 to Zm by their expectations given the observed data x and the current value of the parameters. Okay, so finally, you see, to obtain these values, we just need to be able to compute the expectation of Zi given x and given theta t. How do we do it? Actually, the answer is given in our Gaussian mixture model, which is what we have on here. You see, this is what we did last time. So we can obtain this probability of x Zi being 1 given the xi. And what we need here is actually equal to it. So this is just equal to expectation. The reason is Zi is binary. So for a Bernoulli binary random variable, its expectation is equal to its probability of equal to 1. Okay, and then you see we derive the formula as this, right? So now what you can do is that you just put the current values of P, which is PT, and sigma 1, which is sigma 1t, and mu 1t, and so on into this formula. And that's your conditional expectation of Zi given xi, given x, and given theta t. So what I mean is that in the E step, you're going to do this computation based on this formula. And in the M step, you're going to use your existing MLE formula for the log complete likelihood here, as in here, and then you update the 5 parameters. And with the updated parameters, next step, we go here, use the updated values to redo the calculation of expectation of Zi given xi and theta t. So that's how everything goes. But the key thing is that here the likelihood is having a special form. So in the log complete likelihood having a special form. So once you take expectation of the log complete likelihood, the expectation can enter the summation of I, and then you're just left with computing the expectation for Zi. That simplifies this whole procedure. Okay, so I'm saying that this imputation idea works for this type of log complete likelihood form, where you have in the sum, Zi is just a term being multiplied by something else. But if Zi is not by itself, like Zi is in some complicated function, then you may need to get more expectations in order to calculate this. So I'm saying that this imputation idea is not held in general, but it holds for this Gaussian mixture model case, because the log complete likelihood just have Zi and 1 minus Zi out there. Okay, does that make sense? So sorry that I made some mistakes in the beginning, but hopefully we clarified everything. So I think the key is that MM algorithm is the essence. Yep, please go ahead, Aditya.
I just wanted to ask, so those the parentheses, like the dots in there, those don't change, right? Because those aren't dependent on Zi. Exactly. They just kind of, okay, thanks. Yeah,
those don't change. Yeah, exactly. If you go back here, because these things don't change with Zi. They are just constants, right? Yeah. But to fully understand EM algorithm, I would say the key is that you first need to understand MM algorithm. That's the starting point. And then to understand why the E step gave us a lower bound, you need to actually know the Jensen's inequality. That's the key. And finally, to understand the equality condition in Jensen's inequality, that is why this ratio becomes non-random, you need to know this conditional probability thing. So when you set the distribution of Z to be this density, they cancel out, so Z is gone. So then you're left with a term that's not related to Z, so it's not random anymore. Okay, so I think EM algorithm is very smart because it actually allows us to use the MLE result from the complete likelihood case. So we make the computation very easy. You just need an iterative algorithm. But as we said, you cannot avoid that convergence to local maximum issue because that's just the nature of the MM algorithm. Okay. So any more questions before we conclude? So once we return next time, hopefully I'll try to clarify anything I didn't make clear today. And so we know what an EM algorithm will look like. Okay, so if there are no more questions, I'll see you on Wednesday. And just to summarize, the EM algorithm allows us to estimate the parameters in a Gaussian mixture model using just X. We don't have Z. And then with those estimates, we still go back to here to calculate those probabilities using our parameter estimates. That's the value when the EM algorithm converges to. And then we are going to use those probabilities to assign each observation to a cluster. Okay. And I think the EM algorithm is very, very popular in a lot of bioinformatics methods, if you check it. Because we are dealing with latent data, mixing data, a lot of cases, right? That's the nature of unsupervised learning. We are not supervised because we don't observe the labels. Okay, so I'll see you on Wednesday. Bye. And we have, okay, sure. Yeah, so I will stop the recording. And if you have questions, please stay in the Zoom.